Hello everybody, welcome to chapter 4. We're starting to talk about antiderivatives today. What we're going to be doing is we're going to write the general solution of a differential equation, and we're going to use basic integration rules to find antiderivatives. And really, what is an antiderivative, right? Well, what I'd like to do first here is just kind of go through some quick examples, and we're going to find antiderivatives, and then we're going to discuss kind of what they are. So let's just go through some quick sort of examples. So let's say we were given a derivative, f prime of x equals 2x. And what I want you to do right now is just kind of think. Let's think about what this original function could be, right? What original function could I have had to get a derivative of 2x? And here's what we could have gotten. Our original function could have been x squared, right? Because the derivative of x squared is 2x. So that's how that works. Let's try one more that's not too bad here. What if we had f prime of x equals cosine of x, right? What derivative could have had, what function would have a derivative of cosine x? And when we think about that a little bit, we think about our rules of derivatives, and we remember that the function that has a derivative of cosine x is sine x. And what we've done right here, these two are actually antiderivatives, but what we're going to add right at the end of them is a little plus c, and I'll explain why that's important in a minute. But again, I want to reiterate that these two things we found are actually called antiderivatives. Let me, write that a little bit more clearly so you can see it a little bit better. All right, this is the word I'm trying to say. Antiderivatives. Okay. And just like they sound, they're kind of the opposite of derivatives, right? They're the original function we could have used to arrive at this derivative. So pretty fun stuff. What I'd like to do is get a formal definition in here. I mean, what would calculus be without some formal definitions that we don't really understand at first, but we do later? Okay. So, formal definition. Antiderivative. So, antiderivative. There we go. There's that word again. So, what we can say is big F is an antiderivative. Notice I underlined the word and. We'll get to that in a second. Of little f on an interval I when f prime of x equals f of x for all x in I. And once again, I always just say that this is what definitions are, right? They're just the fancy way, the math speak of saying what we just did up here. The derivative, right, the f prime of these things is the original f that we had. So vice versa, they just kind of undo each other. That's what an antiderivative is. It undoes what our function was that we started with. Okay. And what I want to point out also is the reason that I underlined this word and here. F is an antiderivative. And what that means is this letter C. And what I mean by a C here is constant. Basically, yeah, I could have started with x squared plus some constant, because remember, the derivative of a constant is just 0. So no matter what constant value is here at the ends, the derivatives would be the same. So when we make these antiderivatives, we're always going to put this plus a constant at the end, and we're not really going to specify what that is all the time, because it doesn't matter. The constant, if we took the derivative of it, it would just go away and we would arrive at the same function. So that's why you're always going to see that plus c at the end, and that's not the last time I'm going to mention that in this video. I'll keep mentioning it. Alright, so let's talk about, let's talk about that constant of differentiation. That's what we call that C value I was just talking to you about, the constant of differentiation. And let's just go through a little quick example here. So find the antiderivative so f of x equals 2x. And what we can do here is kind of go backwards. We already did this one up there, but we know that the antiderivative would be x squared, and again we have that plus c. And here's why we have the plus c. Let me just give you a quick example of what I was just talking about. Let's look at some examples. So say if I had x squared plus 7. Let's say I had x squared minus 5. Let's say I had x squared plus 10. I'm not sure. It really doesn't matter. If I took the derivative of all these things, d dx, check it out. I get 2x, 2x, and 2x. Oh my gosh. For all those different constant values I filled in, I got the same answer. So this is what we call like the general antiderivative, or an antiderivative, when we just put the plus c at the end, because it does not matter what we actually put in for the c. The result is always the same. Okay. Moving on. Let's talk about a solution of a differential equation. And it's basically, we're answering the same question, it's just going to look a little bit different at first. So let's call this just an example. And we're going to say find the general solution of the differential equation. I'm not sure if it's grammatically correct to put colon, but I don't really mind. Y prime equals 2. And so what this question is asking, it isn't that obvious about what it's asking, but here's what it's saying. It's saying y prime is 2. The derivative of y is 2. So what could I have started with? What could y have been to make its derivative 2? And that's an antiderivative that we're going to answer with. So what the answer would be there is y equals 2x, right? This could be, if I took the derivative of this, I would most definitely get 2. So this is my answer to this differential equation. I want to know what y was to get this derivative, and y was 2x. And remember though, I have to include that all-important plus c, because there could have been a constant there too. If it was 0, that wouldn't matter, right? Or any other constant value. If I took the derivative of this, I would get 2. And I really want to stress plus c. This constant differentiation is so important. Highlight it in your notes in some capacity that plus c is like, I'm going to say uber. I haven't used that word in a while. Uber important. Because, you know, our end game is that AP exam, and the AP exam is very, very picky about this. Uber important, must report in your answer on the AP exam and every assessment that you take in my class. So make sure you're always putting your plus c at the end of your antiderivatives. Okay. Let's look at integration notation. What integration is finding the antiderivatives. It's the process of finding the antiderivative. So I'm going to set up something. We're going to have y, and this kind of like fancy curly Q, f of x dx equals big F of x plus c. Okay. And here's what all these parts mean. This curly Q is called an integrand. And that's what's telling you that you're taking an antiderivative, this little guy right here. Okay. And we call this the variable of integration. Variable of integration. It tells you what you're taking the integral with respect to. And then this big f of x is just an antiderivative, right? Something that could be an antiderivative. Oh my goodness. Antiderivative. Oh dear. Ative of our f of x. And then plus c, that all-important constant of integration. Okay, and that's really what all of these pieces mean for an integral. And what we're going to do with that is we're going to practice using this notation. And again, integration is just the process of finding that antiderivative, which we've done in the last few examples. So let's get started with a first one that looks like this. Let's say we have an integral and we have 3x dx. And we want to find, this is telling us, we want to find the antiderivative of 3x. And here's what we can do. And what I'm about to do is I'm about to use some rules of integrating, and they're very familiar to the rules of differentiating. And I'm going to write a page number down right here so you can find where I'm getting these rules from in your book. So I'm not going to write out all of them because there's like 20, and I'm not going to do all that writing. But on page 282 in your textbook, they're all listed out for you, and they're paired with their corresponding differentiation rule, so it's really nice for you. But I'm going to do a few examples, and I'll highlight which rules I'm using. So to find the antiderivative of this, you might just be a pro and you might know what this is at the top of your head, but I'm going to introduce a few rules for you right now. First of all, whenever we have a constant in front of a variable right here, what we can do is take that constant outside and just have x dx that we're integrating now. And what we can do here is still have the 3, and I'm going to rewrite this as x to the first, just so we kind of understand where we're going with this. And what I'm going to do next is I'm going to use a rule of a rule of integration. And the rule of integration I'm going to use is called the power rule, but it's a little bit different than the power rule for differentiating. And here's what it says. The power rule of integration says if I have an antiderivative of x to a number, then I can do x to that number plus 1 over that number plus 1 and plus c. Always got to have my constant differentiation. Okay, and so what I'm going to do now is I'm going to do that with this 1 here. I'm going to rewrite this as 3 outside x squared over 2. And then I'm going to say plus c. And I can simplify just a little bit here if I do 3 over 2 x squared plus c. And that is my antiderivative. Not too bad. All right, let's do another example on a separate sheet of paper. Great. So let's say we had 1 over x cubed dx. It's going to help to rewrite that first. And so what we're going to do is we're going to write the word rewrite. And we're going to say not 1 over x to the third, but x to the negative 3 dx. And now what we can do is the same rule as last time. We can do that power rule. So we're going to do x to the negative 3 plus 1, so x to the negative 2, all over negative 3 plus 1, negative 2, plus c. And when I kind of simplify that, make it look a little bit pretty, I have negative 1 over 2 x squared plus c. There we go. Again, I'm always writing my plus c's. You got to do that when you're writing these antiderivatives. Got to make sure you write your constant of differentiation. Okay. Let's do another one. Let's take the antiderivative of square root of x. Again, rewriting is always very helpful, just like it is in differentiating. I'm going to change that to x to the 1/2. And again, I get to use that power rule of integration. So I'm going to do x to the 1/2 plus 1, which is x to the 3/2, all over 3/2, right? Because 1/2 plus 1 is 3/2. And I still have my constant differentiation plus c. Now remember, dividing by a fraction is the same as multiplying by its reciprocal, so I'm going to have 2x to the 3/2 all over 3 plus c. And that is my answer. Alright, let's keep on going. Let's say that we had, a trig example. This would be fun. So let's say we were doing the antiderivative of, 2 sine x. Well, I'm hoping that this is kind of a familiar process as it was with differentiating. I have this 2 in front, so I can actually just put that in front of everything, take out my constant, and do the antiderivative of sine of x. And you may have kind of put this together from the differentiation rules of sine x and cosine x, but the antiderivative of sine x is actually going to be negative cosine x. So I'm going to have 2 times negative cosine x plus c. And when I distribute that out, I get negative 2 cosine x plus c, and that's my antiderivative. Okay. Alrighty, so there's one more quick one that I'd like to go over before we get to a new topic. Let's say that we wanted to integrate 3 over x. And again, what I want you to see here is that this 3 is actually a constant on top. And what I can do then is take that and put it out in front, and then I have 1 over x dx. Now, I want you to just think about this for a second. What differentiation rules do we know about the fraction 1 over x? And it's not power rule, it's actually natural logs. Remember that the derivative of natural log is 1 over x, so what we're going to do here is change this, make this equal to natural log absolute value x plus c. Again, I just want you to understand that that's kind of a familiar interchange there between 1 over x and natural log x, because we know the derivative of natural log x is 1 over x. That's something we should be familiar with by now. Okay. And I can just drop those parentheses and say 3 natural log absolute value x plus c. And again, this is a rule that's on that page in your textbook. You can go through, take a glance at those. Please do before tomorrow's assignment. Okay. Next, let's start talking about polynomial integration. That's an I, my goodness. Integration. Okay. Let's do an example. Alright, so this one's kind of silly. It doesn't look like much, right? It just kind of looks like we're taking the derivative of dx. What? But we're actually doing taking the integral of dx, but we're actually doing the integral of 1, and we know that the derivative of x is actually 1, so when we take the antiderivative here, we get x plus c. So you rule to know, whenever we have a 1 in the integral, the antiderivative is just x. Okay. Let's do another one, separate sheet of paper. Okay. Let's say we had a bunch of terms, though, not just one thing going on. So let's say we wanted to know the antiderivative of x plus 2. If we wanted to know the integral of x plus 2. What we can do then is we could split that up as the integral of x plus the integral of 2. Okay. And what we can do here is use that power rule. Power rule is going on here. I actually have x to the first. I'm going to kind of write a little 1 in there so we remember that. And what I'm going to have then when I take the antiderivative, I'm going to have x squared over 2, because 1 plus 1 is 2, and on the bottom. And then another good rule for you to know is when you have a constant in there, you just do the constant and an x. So this is just 2x. And we have to include the all-important c at the very end. And that's a good thing for you to do. Find out what each piece is going to be, and then throw your c on at the last thing, just so you don't forget about it. Always make sure it's there very last thing when you're reporting your answer. Okay, let's do another one. Ooh, this one's more fun. So let's say we were taking the integral of 3x to the 4th minus 5x squared plus x. Well, what we can do is first simplify, right? I have a constant and I have a constant, so let's put those out front. Let's say 3 and the antiderivative of x to the 4th minus 5 times the antiderivative of x squared. And then plus the antiderivative of x. Okay. And so what we're going to do now is use the power rule, and we're going to have 3 times to the 4 plus 1, so 5x to the 5th all over 5, minus 5 times x squared plus 1, so x to the 3rd over 3, plus what we have here with the derivative of x is, or pardon me, the antiderivative of x is 2x. And from there, what we get to do is write our plus c. Okay. And we can make that just a little bit neater if we make these fractions instead of just numbers multiplied on the outside. So we're going to say 3x to the 5th, 3x to the 5th over 5 minus 5x to the 3rd over 3 plus 2x plus c, and we'll call that good. Okay. Let's talk about rewriting. Oh, pardon me, my sleeve keeps catching this paper. Alright, so if we had, say for example, x plus 1 over radical x dx, what we can do is first rewrite. We can say that we're taking the integral of x over x to the 1/2 plus 1 over x to the 1/2, and the whole thing has the dx attached at the end. Okay, I'm going to add in a little bit of something here so I can understand how the simplification happened. What I really have on top, even though it's not typically written, is x to the 2 over 2, right? X to the first is x to the 2 over 2. And remember, when I have the same variable with different powers, I get to kind of do their difference. So 2 minus 2 halves minus 1/2 gets me x to the 1/2. And then I still have this guy, but I can change 1 over x to the 1/2 to x to the negative 1/2. And now this is just a little bit neater to take the antiderivative of. Okay. I can use the power rule once again of integration. So 1/2 plus 2 halves, or 1/2 plus 1, I get x to the 3/2 over 3/2 plus x to the negative 1/2 plus 1, so x to the 1/2 over 1/2. And what happens then is I get my 2/3 x to the 3/2 plus 2x to the 1/2. Alright, I'm going to write plus c at the very, very end here, but I am going to keep simplifying, so I'm just going to kind of bring my work up here. Okay. What I can do next from this is we can kind of see that they both have some similar stuff going on. They both have an x to the 1/2 at least, and they both have a 2. And what we can actually take out here is a 2/3 and an x to the 1/2. And when we do that, what we're left with inside when we factor is an x. And we really have an x to the 2 over 2, right? Because 2 over 2 plus 1 over 2 gets me 3 over 2. But remember, 2 over 2 is just 1, so just write x plus, and then I'm going to write 3. Because down here, when I took out the 2/3, the x to the 1/2, I took out the x to the 1/2, I took out the 2, and because I took out a 2/3, when I multiply this back, the 3's will cancel, and I'll get what I started with originally down here. Okay. And then what I get to do is just simplify one little piece more, 2/3 times radical x outside x plus 3. And that's really all I can do. And I write plus c at the end because I'm done finding, I'm done simplifying, and I need to include my constant of differentiation. Okay, or my constant of integration, pardon me. Okay, let's do, one more fun example with some trig. That'll be fun. All right. So let's say we were doing the integral of sine x over cosine squared x dx. Okay. What we can do here is split this up. We can split this up as 1 over cosine x times sine x over cosine x dx. And here's what we get to do with that. What we have going on is we get to remember that 1 over cosine x is the same as secant x, and sine x over cosine x is tangent x. So this is really what we got going on in our integral. And to take the antiderivative of this, it's important to remember a property or a differentiation property of secant. So remember that the derivative of secant x is secant x tangent x. So what we can do is kind of take this derivative rule and use it backwards, right? If we have this, then we know the antiderivative of this is secant x, right? If we have that as our result, we know we must have started with secant x. So when I take the antiderivative of this piece, I know I'm just going to have secant x and always plus c. Okay. And that is all I have to show you in this first video. Thanks for watching. We'll see you in class tomorrow.